So, okay, I'm giving two talks, and so the first one was supposed to be introductory, so I'm going to say some relatively introductory things, hopefully, and then next time get into some more recent research. But just to be clear about what we're talking about, so we're going to fix a compact Lie group G. And for me, and for much of this talk, G will often be a very simple compact Lie group, maybe something like a finite cyclic group, even a finite cyclic group of prime power order, or maybe G equals the circle. So in my limited experience, 90% of the time I'm working with one of these groups. And when you have any compact Lie group, including one of these simple ones, there's an associated space. And by space, I mean something like a homotopy type, or maybe now that I'm in Europe, I should say an anima or something. An associated space BG, such that the loops on BG are G. And this space, being a homotopy type, can be thought of as an infinity groupoid. So we can think of it as a certain kind of category. And then the infinity category of functors from BG to spectra is sometimes known as the category of spectra with G action. Or if you prefer, it's also known as the category of Borel G-spectra. So to me, and hopefully to you, these terms are synonymous. A Borel G-spectrum is a spectrum with G action. It's just a functor from BG to spectra. And you can think about this as a local system of spectra varying over the space BG. Okay, and then what are the kinds of invariants one extracts from a Borel G-spectrum? So given some functor, x from BG to spectra, one can extract certain invariants, and the most important are the fixed points, which are the limit over BG of the functor, the orbits, which are the colimit over BG of the functor, and then a last and somewhat more obscure one is the Tate construction, which, at least for G finite, is the cofiber of a canonical map from the orbits to the fixed points, and the norm map. These Tate invariants can be defined even when G is not finite, though it takes a slightly more complicated form. So this kind of definition came up for me as a student when I was learning about some specific examples that are of great interest in chromatic homotopy theory. So maybe the most basic is Ku with its action of complex conjugation, which is an action of this cyclic group of order 2. And maybe I'll complete my Ku because I like to think of Ku as something like Morava-E theory. And something we'll probably see later is that in general we want to be studying something like a Morava-E theory with a G action, of which this is the most basic example, where G here is a finite group. And here this is a Morava-E theory. So as Vesna may explain, I feel like a lot is being put on Vesna here. These E theories with finite group actions are the basic building blocks from which one can build the KN local sphere and then eventually the sphere itself. Okay, so I was very interested in these. At some point I also learned about MUR, which is this thing that Marcus wrote as MR and said he would not talk about. But this is got a C2 action on it that comes from a complex conjugation of complex manifolds. So it's compatible with, say, the C2 action on KU. It also has to do with complex conjugation. And right, the other basic example that comes up a lot in my areas of study has been Hahn homology of a ring with its Borel S1 action. So I expect we'll see these examples come up again and again, and it's not so important if you don't know what this is yet. It'll be explained later. But these are all really Borel G-spectra. I'm not yet talking about genuine G-spectra, and it's sort of an observation maybe of Nikolaus and Schulze that just knowing this is a Borel S1 spectrum is enough to do everything one typically wants to do with Hahn homology. Okay, I feel like these examples of Borel spectra are very important, and they were very motivated for me as a student, as well as this notion of Borel spectra. It was slightly, oh yeah, maybe I should just quickly remark what some of the invariants are. So the Tate construction of this is 0, fixed points are KO, and then maybe the interesting thing, the Tate fixed points of M are MO. So that gives us relation between MU or MR and MO that Marcus promised.
If you're writing it KU, if you wrote KUR, that would be
more compatible.
correct.
You would feel better.
I think it's a bit misleading to write KU to the TC2 as 0. I mean, if it was just...
Let me write that to mean the same thing I meant previously. So I'm going to distinguish that from KU sub C2, which maybe is more familiar. Okay. All right, but there's a sort of, to me, took a while for me to really feel like it was a motivated notion. It's a notion that's sort of maybe the center of this conference and semester is to study genuine equivariant homotopy theory as opposed to this Borel equivariant homotopy theory. So maybe just to note, BG is rarely a compact space. Right, so if I look at something like B, the cyclic group of order 2, that's RP infinity, which is far from a compact space. And as a result, the category of Borel G-spectra, which is this category of local systems on BG, sits fully faithfully inside of a bigger category of genuine G-spectra. And if these constitute local systems on BG, these may constitute some kind of constructible sheaves on a compactification of BG. But maybe let's just see what that looks like in the most basic and most prevalent example. So for any prime P, a genuine CP spectrum, we're looking at the cyclic group of order P, a very simple group, is the data of Well, you have an underlying Borel CP spectrum. You have more than the data of a Borel CP spectrum. You also have an additional spectrum, which is called phi CPX. Showed up in Marcus's talk. This is the geometric fixed points. And that's required to have a map. Some gluing data in the form of a map spectra to this Tate invariant. And so that's it. It's the data of a Borel CP spectrum, but with this slight additional thing of just a spectrum without any action and a map to the Tate construction. Okay, and from this, one defines the genuine fixed points. As a pullback, we have a genuine fixed points, and as a pullback of this diagram involving the geometric fixed points, the Tate fixed points, and the homotopy fixed points. We recall that the Tate fixed points are the cofiber of some map into the homotopy fixed points, and therefore there is a canonical map from the homotopy fixed points into that cofiber. And these genuine fixed points participate in a kind of Mackey functor with the underlying spectrum of X, underlying Borel object, which we saw a little bit of in Lor's talk, and maybe we'll see some more of in Clark-Barwick's talk. Okay, the other thing I wanted to just remark is that Borel CP spectra sit really faithfully inside genuine CP spectra as those genuine X for which the map from the geometric fixed points to the Tate fixed points is an equivalence, so that the geometric fixed points constitute no extra data, and they're simply a repackaging of the Tate fixed points. Okay, so basic example of a genuine G-spectra that is not Borel is this object that Marcus discussed. We can look at MUCP, this genuine equivariant MU, and it consists of the following things. So I have to tell you a Borel spectrum and then its geometric fixed points. And the Borel spectrum will just be MU with trivial Borel CP action. In other words, I take the constant functor from BCP to spectra, whose value is mu. That's somewhat boring as a Borel spectrum. But as a genuine spectrum, I can make it somewhat more interesting by doing something with its geometric fixed points. And so I need to give you a map. The Tate construction of this trivial action, and I can declare this spectrum to be anything I want, and the thing it winds up being is mu tensor MUP tensor p minus 1 times. And this is the usual mu, and this is the periodic mu. So you will notice, for example, that this is not connective, which is something that Marcus highlighted. So let me not say too much about what this map is, but let me just observe that pi star mu tate CP is very calculable. This is just mu star, i.e. the Lazard ring. I join a power series variable, and then I invert that power series variable. I mod out by the p series. And well, that's calculable, and it's somewhat of an ugly expression. It's not anywhere near as simple as the homotopy groups of this object, which Marcus pointed out are a polynomial ring with a few generators inverted. So this is more complicated. And homotopy groups of these geometric fixed points. And in particular, it's not equal to the homotopy groups of the geometric fixed points. So this is really a genuine CP spectrum and not a Borel CP spectrum like some of the other examples. So there's a lot of reasons to care about equivariant homotopy theory in the genuine sense as opposed to the Borel sense. I hope we'll see more of them as the week progresses. We already heard a little bit about using genuine equivariants to understand equivariant manifold theory. And we hear, I think, a little bit about equivariant K theory and equivariant kinds of TMF. We also maybe got some hints that there's some really interesting questions arising from symplectic topology that interact with equivariance in forms that led, for example, to this recent result of Abu Zayed and Bai that was mentioned in Marcus's talk. Okay, but for me, I didn't particularly care about genuine equivariance as a student. I cared about these kinds of examples that were Borel equivariant. And I came to know and appreciate genuine equivariance because oftentimes one finds that to understand Borel G-spectra, one often resolves them by genuine G-spectra. So I'd like to indicate a few places in which this kind of philosophy rears its head, where in general, in homotopy theory, we're often constructing spectral sequences by means of resolutions. And it turns out that some of the most powerful resolutions that we can use to study Borel G-spectra are naturally made out of genuine G-spectra. So maybe I'm just going to bite the bullet and write a few definitions, which we will then explore later. Let me give a few definitions and constructions, which maybe some of these are folklore, but some will be appearing in point work with Sanaf Delwapkar or Panraxit. I'm just going to formalize a construction.
Can I ask you something? Is there an analogous description of genuine G-spectra for finite G, analogous to your examples there?
Oh yeah. I meant to mention that there are analogous but increasingly complicated ways of describing genuine G-spectra for more complicated groups G.
That's good.
In that spirit, yes.
But you don't want to.
I don't want to at this time. perhaps at any time. Yeah, so I'll explain more complicated groups as needed. Okay, let me make a few definitions. So let's say a G equivariant spectrum X is even if for all H and G, all subgroups, and all complex H representations V, I look at pi V H minus 1 of X. Okay, so this means H equivariant maps into X thought of as an H space from the one-point compactification of the representation V, but D suspended once. And there's a sort of very important example to keep in mind here, which is
Allow virtual representations here.
yeah, let me allow virtual representations. So this is I mean, I'm calling it an example, but it's a big theorem of Haussmann.
Do you really want virtual representations? Because otherwise, then you don't need to go -1.
No, I mean complex representations. So 1 is not a complex representation, it's only a real representation.
Will this force other RO not in the image of complex grading stage?
Not in general, no.
Because they're not complex oriented.
Not complex oriented. I mean,
okay, not in general.
I mean, they're pretty close to saying a complex oriented. Maybe the only thing that's missing is some level of periodicity or something.
Well, complex oriented could have stuff in this.
Right, okay, so even is going to imply complex oriented, almost, but not the other way around. Okay, but a theorem of Marcus is that for compact abelian G, mu G even in this sense.
But that's not my.
Well, okay.
Let's take it up that.
I was going to name some other names, but you tell me exactly which ones.
Thank you.
Which names I should put.
Put left that.
I'm going to pretend I know how to spell that. Okay.
Maybe what you complete to have a guess it's
Yeah. Maybe with
I'm also going to mention geocliche. I'm going to mention
just
green.
go in order.
I think you should stop with that.
Yeah, okay, maybe, but let me say that I also care, at some point about what these groups are, that there's this equivariant Lazard ring that
Depends how big.
let's say that it's even with understood homotopy groups. And then people might be slightly less modest. I'm doing on. Okay. All right. So there's some notion of what it means to be equivariantly even in genuine G equivariant homotopy theory, which I'm going to attach to complex representations, not real representations. And so let me make another definition. A map A to B of G equivariant E infinity rings. G equivariant rings in some form is evenly free if B can be built in the category of A modules by attaching A module cells of the form sigma VA, where V is complex. So you attach complex representation cells. All right, and then we're almost to the idea here. So fix.
So, I'm sorry, is this the subquotients like sigma VA, or is it a map from sigma VA to A?
The subquotients would be a direct sum of sigma VAs. Okay, so these two conditions play nicely in that if you tensor something with even homotopy with something with even cells, it splits. So that's what this is designed to do.
Sorry, what is meant by G equivariant E infinity rings? E infinity rings after getting GH.
So I think it's just corresponds to what was called a green functor. So I mean just an E infinity ring in the symmetric monoidal category of G-spectra. I think you could get away with more or less. It really won't change. Like you can fiddle with these definitions in various ways, and it won't change any of the interesting examples. So let me. Right. So fix G equivariant E infinity ring A, and suppose there exists an evenly free map A to B with BU. So I'm just going to suppose the existence of such a thing for my fixed ring A, and then I'll say that the G equivariant even stack for BGA is that associated to I star BG be a tensor over A bullet plus 1. And the G equivariant even stack for maybe the genuine fixed point is that associated to pi star B tensor dot plus 1 fixed point, the infinite. In other words, maybe I should be writing this. So what do I mean here? So if I have a map of E infinity rings, less than that, I'll get a descent object. I'll get a cosimplicial object, and then I take pi star of that kind of cosimplicial object, and I get a Hopf-algebroid, or in other words, a stack. And the Hopf-algebroids or stacks here will be converging or trying to converge to calculate the homotopy groups of these invariants respectively. So in favorable cases, these will converge, and there's a little lemma that this does not depend on the choice of B. this is an invariant of A. It's an invariant of A. I'm just assuming there exists some A to B map with B even, but the claim is that these stacks do not depend on that choice. Just a big example. That if G is compact abelian, the map from the sphere to MUG is evenly free with even target. Right, so to say that it has even target is this claim we had here that it's got even homotopy groups. Who knows who proved that? Maybe someone who starts with an L. I don't know. This claim is not that much more complicated. You just have to understand what the cell structure of MUG is in the category of S modules. MUG is a Thom spectrum over BUG, so its cells will match the cells of BUG. And BUG has a Grassmannian model. It's well understood to have representation cells. Okay, so that tells you that you can compute some stacks associated to the sphere using this map. So, example, G is the trivial group. We get MFG, the moduli of formal groups, because this is the stack associated to the non-equivariant map from the sphere to MU. And this is for both SE and SPE, because they're both here. What about a more interesting example? Well, maybe before I go to the more interesting example, I should just remark that this S to MU descent that we get up to P completion is related to cellular C-motivic spectra. Just if you like that kind of thing and know what I mean by it. No worries if it's unfamiliar. So then another example. So if I take the CP equivariant sphere mapping to MUCP, what do I learn? I learn that the stack associated to PCP of S, which is just S, is the stack associated to taking the Adams resolution of this map, and again this was MU intrinsic MUP P minus 1 times. Right. And if I look at the atom spectral sequence associated to this map, this is just MFG. So MFG we usually think of as coming from the map from S to mu. But if I look at the atom spectral sequence associated to S mapping to some tensor products of MUs, it's also going to give you the same stack. The Hopf algebroids will be equivalent from the E2 page onwards. So this is just some inefficient presentation of MFG. I want to contrast that with
Jamie, could you raise that word?
So it's just an inefficient presentation of MFG. So maybe just a note is that up to a sort of mild P completion, the sphere is Borel. This is what's called the Siegel conjecture, the theorem of Lin or Gunawardena at odd primes. And here, what I'm doing is resolving a Borel spectrum by genuine spectra, by this MUCP. And if I didn't know about the category of genuine spectra, if I just tried to naively associate a stack to the Tate fixed points of S, which are equivalent to its geometric fixed points after P completion, I might look at something like mu dot plus 1 Tate CP and try to compute the homotopy groups here. But here the objects you'd get in your Hopf algebroid would be power series. It wouldn't even be clear what it means to take spec of them, especially because the power series variable gets inverted, so it's just not even clear what it means to take spoof of it. So it doesn't really fit into the language of algebraic geometry or formal algebraic geometry to associate a stack to this kind of object. So there is no clear stack or even formal stack attached to pi star of this co-simplicial object. And so we somehow allow ourselves to obtain something that's really classical algebra geometry as long as we allow ourselves to resolve our Borel object by genuine equivariant objects. And I'm not here choosing MUG and saying that's my favorite thing to resolve things by. I'm saying it's coming out of some machine, which maybe this is the only example we've seen so far. But I hope over the remainder of this lecture and the next to convince you that this machine gives you interesting answers, not just when you plug in the sphere. And you might not need to know about MU to evaluate its outputs. Maybe another remark that the stack associated to these genuine fixed points is presented by pi star of MUCP dot plus 1 CP. Doing this. And I think Marcus is probably going to talk a lot about this in his next talk. this is the moduli of CP equivariant point groups, to be explained later. Okay. So I said that when you have a trivial group, the descent you get is closely related to cellular C-motivic homotopy theory. And maybe let me prematurely highlight some work in progress of Eta Allen and Lucas. All right. How do you say your student's name?
Not sure I'm doing it right now. TSO.
Okay,
I would say.
I'm going to put that on you.
I'm not French.
So I'll just say that this aims to connect descent S to MUG. Let's just say CP for simplicity with cellular CP equivariant C-motivic homotopy. This is a pre-existing notion. There's already a theory of CP equivariant motivic homotopy theory in the literature, due to Mark Hoywa, I think. So I think we're clearly on the right track with what we're doing if we discover that we match up with the pre-existing motivic literature, what is expected from this project. And I'll just also say that some of this is based on some ideas, which are also work in progress. For and Venkatesh, I spelled that right, which who study the stacks associated to simple rings like, say, Eilenberg-MacLean rings for complicated connected compact Lie groups. So you should ask them for the outputs. But as I said, this is a machine where you take in any equivariant E-infinity ring and you spit out a stack. You can do that for a simple equivariant E-infinity ring over a complicated group, like a connected compact Lie group. My understanding is that they're recovering from this construction many stacks that are already quite familiar in geometric representation theory and in the geometric representation theory literature. So that might be a cool connection. In any case, let me maybe
Which complicated compact connected Lie groups?
oh, I don't know. You should ask them. But for example, starting with things like SLN, which are maybe not so complicated, not so compact.
Is it too many?
Yeah, so I think they're recovering some pretty interesting stuff. But it is premature, especially for me, to be talking about it. so I guess what I'll talk about next and continue on with in the second lecture is following proposition. The natural map THH of mu to MUCP is evenly free, even target. So in a moment, I'm going to tell you what THH of mu is. And I'm going to think about it as a genuine CP spectrum, even though I said it's Borel. In fact, it's going to wind up being a Borel genuine CP spectrum. But when I write down this map, I'm not resolving it purely in terms of Borel objects. I'm writing a map from a Borel object to a not Borel object, and that's going to let me understand this using algebraic geometry. It's exactly like the sphere. So I'll remind you what this is as a CP spectrum in a moment. Again, it's going to be Borel. This, we said, was even, so it just remains to check that this is evenly free. In other words, to understand what this looks like as a module over this CP equivariant. All right, so what's the proof sketch? The map here that I'm studying is the Tom spectrum, Tomification of a map of infinite loop spaces. So what is mu sub CP? It's a Tom spectrum over bu sub CP. So there's some map from bu sub CP to the Picard group of the sphere, Picard spectrum, and this infinite loop map, it's Tom spectrum. It's the J homomorphism is MUCP. And then what is this THH? Well, you can look at S of lambda plus tensor BU mapping to BUCP. So this is the lambda is my notation for the complex plane being rotated by e to the 2 pi I. So that's an S1 equivariant representation that I can view as a CP representation. And I'm
to the 2 pi I over C over P.
P. I mean over P.
It's a representation of CP.
I want it to be a representation of. I mean, when I restrict to CP, I want it to be that representation. I think it's a. So I claim there's a canonical map like this, which comes from restricting something I think defined over S1, where this is literally induced. So this is just some map of spaces. It's canonical because this is induced, say over S1, and I restrict to CP. And then I'm just tomifying that map, and that gives you this map. And it's a theorem of Rodness that the object here you get, say, up to a mild P completion is, in fact, Borel. So this is Borel. Even if you're thinking about these all as genuine things, you wind up with a Borel object here. Yeah.
Intentionally no CP on the MU inside THH.
Oh, well, so this is induced. So somehow, like, it doesn't matter what, I mean, I can put a CP here. This THH operation forgets about the action on its input because it's like an induction. It's a norm. And so it forgets the action. Okay. So we have this map, and so now I'll just observe that there's a fiber sequence of infinite loop spaces. S of lambda plus. I I should say this doesn't depend on the input CP action, but this map depends on the input. And then the cofiber is B lambda, BUCP. The lambda delooping of this infinite loop space. And this just comes from the fact that there's this cofiber sequence that Marcus wrote. I like to denote like this. So I'm tensoring that with some spectrum and then taking loops infinity and getting a fiber sequence of infinite loop spaces. And so what that implies is that mu sub p has a THH of mu module has cells of the space C lambda DUCP. Manipulation of Hahn spectra. And so if you want to know that this is evenly free, you have to check that the lambda delooping of BUCP has representation cells. So the lemma, I don't think is recorded anywhere in the equivariant literature. I'd like to know if it is. It's that B lambda UCP is the same thing as BSUCP, which is an object that is understood. And in particular, it can be seen pretty easily that it has maybe even cells, or at least is a retract of something with even cells, because it's a retract of BU. Okay, and that's all you need to finish this proposition. So maybe I'll remind you of some of this next time, but I have a question. So what V is loops infinity suspension V vector cover U G have representation cells. This is maybe for compact abelian V. And then what about loops infinity suspension V and UG? And then maybe what is the connection between the kinds of things that some of you might recognize me hinting at here and unstable G-equivariant motivic homotopy theory, which again is an already existing notion and that we can feel very happy about when we connect to, as a sense that we're sort of doing something very sensible. We connect to an already existing motivic notion. So I've got 5 minutes left. Maybe I'll stop here.
The rep cells means for complex representation.
Yes, complex representations. Yeah, so I have plenty to say about the other notion of evenness you might have thought about, but let's stop here.
Questions?
Will you tell us something about the stack associated to this resolution?
Yeah, so my goal is in the second talk to explain what this stack is and some even more complicated stacks that will eventually lead to hopefully the algebraic K theory of mu.
So what happens if you don't forget the CP action on the mu but take the twisted CP norm? So take the CP norm up to S1 and not TH.
Yeah, I don't know. So maybe that's worth thinking about. I don't know. Yeah.
Could you say anything more about the Moduli connection? Or is that coming later?
Well, I think it's work in progress by people, but the hope is that there's some subcategory of equivariant motivic homotopy theory which knows about this descent that involves equivariant Boydism. Maybe we can talk afterward if that's not clear.
Any more questions?
In the motivic situation, the sphere is Borel or has a signal conjecture if you think of it as being UP equivariant, where UP is that gray group, as opposed to CP equivariant.
So, and one thing is that we're working over the complex numbers where those groups should be the same.
Well, it's after, I mean, the classifying spaces, the entire classifying spaces are equivalent of the motivic. Oh, okay, I'll ask you.
Any more questions? Well, there are none online, so it remains only to thank Jeremy again.